Hello friends, my name is Sushant Rathan and I will be teaching you radioactivity. So this is going to be the first session on radioactivity, and in this session we'll understand what is isotope, how unstable isotopes achieve stability, and what is the two law of radioactivity. So in the first slide we'll understand what are the two types of isotopes. So basically, going into depth, first we need to understand that isotopes are the element having same group, having same atomic number but different mass number, meaning in the periodic table they belong to the same group and same period. That is, if I'm taking first period of first group, then I'm talking about hydrogen only. So all the elements will belong to hydrogen, and then all the elements will have same atomic number but they will have different mass number. As we can see, in stable isotopes and unstable isotopes, all the elements are same: oxygen, hydrogen, carbon and lead, but they are having different mass numbers. Like first we can look at oxygen, it is having O18 and O16. Hydrogen has H2 and H1. Simply in unstable isotopes, we can see lead has one stable isotope. Lead 204 is stable isotope, whereas lead 205, 206 and 208 are unstable isotopes. Okay, so we have seen that there are two types of isotopes, stable and unstable. But how are they caused? So let's look at the figure on the right. Here we can see that we have plotted number of protons with respect to number of neutrons. Now we know that an atom's nuclei consists of number of protons plus number of neutrons. So what we think conventionally is that as the number of protons are increasing from left to right, similarly the same number of neutrons should increase from bottom to top, isn't it? So this would be the theoretical line that should be followed with increasing atomic number. But this is not the case. Instead, in practical, what happens is that number of neutrons increase with a greater rate with respect to the number of protons, or I should say that as the atomic number increases, the number of neutrons increased in an atom's nuclei will be much more than number of protons. Now, when these neutrons exceed at a very greater number, let's say at around atomic number 126, if we take this point, then look at the number of neutrons with respect to number of protons. Actually, sorry, this is not atomic number 126, but rather atomic number 82, as atomic number is determined by number of protons. So if we look at it, 82 atomic number, the number of neutrons are much more than the number of protons. Now this causes the atom to undergo radioactive disintegration. So unstable isotope lead to radioactive disintegration. Whereas if we go for lower atoms, such as let's take hydrogen or oxygen only, then the number of neutrons are not too much with respect to the number of protons, or rather we should say the number of neutrons are not greater in number. As we can look here, the number of neutrons in O18 and O16 system are only increasing by +2, so not much increase. Hydrogen 1 and 2 increase by +1, not a big increase. But if we look at 82 atomic number, then the number of neutrons have increased by almost 18 plus 26. I think it should come out around 38. 38. 40, 44, I think 44. They have increased by a number of 44 with respect to protons. So this is what is causing unstable isotopes. So you have to just keep in mind that stable isotopes, they only undergo mass fractionation. You must have heard in O18, O16 ratios are used to determine glacial and interglacial periods. That is the only change in their concentration. Whereas unstable isotopes, they undergo radioactive disintegration or radioactive processes to attain stability. Now that we will understand in the next slide what are the three major radioactive disintegration processes. So three types of nuclear decay which occur are alpha decay, beta decay and gamma decay, which you must have studied in previous 11th, 12th or even 9th, 10th classes. So in alpha decay, whenever an atom undergoes alpha decay, its atomic number decreases by 2 and its mass number decreases by 4. So the simplest example is samarium neodymium system. Samarium has atomic mass of 147, okay, and atomic number of 62. So to attain stability, it undergoes alpha decay. So what this alpha decay causes is its atomic number will decrease by 2 and its mass number will decrease by 4. So mass number will become 143 and similarly atomic number will become 60, okay. And then a helium particle, as we can also interpret it in other words, a helium particle or an alpha particle of 4 atomic mass and 2 atomic number will be ejected along with some gamma radiation. In beta decay, no change in atomic mass number occurs, but atomic number increases by 1. It is also known as beta negative or negatron decay. So what happens is, let's take RBSR system. We take rubidium. Rubidium has a atomic number of 37 and a mass number of 87. Okay. So during beta decay, its mass number will not change, so we can write it as it is. It will convert to strontium and the atomic number will increase by 1, and a beta negative particle will be ejected from the nucleus. Okay, beta negative. So again here some gamma energy will also be released, and this is our beta decay, only change in atomic number, and that too atomic number is increasing by beta decay. Okay, now gamma decay is even simpler. Like if we take barium 137, here no atomic number or mass number will change. Barium will remain barium. It is just simply that it will emit some gamma radiation to attain stability. So these are the 3 types of nuclear decay which we have to keep in mind, because it is going to be very important in future when we are going to study different types of isotopes and how they undergo radioactive disintegration, or different systems of isotopes. Okay. Now, the third and the most important part of this lecture is law of radioactivity. So see, law of radioactivity is composed of 2 statements. The first statement is there is an equal probability for all nuclei of a radioactive element to decay. This simply means that for an atom, let's say an atom of X to decay, it doesn't depend on the concentration of X in the system. It simply is a probability which is independent of time. Okay, independent of time and also independent of concentration. Means that let's say if X is going to decay to Y in 2 hours, then it doesn't depend on X concentration, or it doesn't even depend on how much it doesn't depend on any other factor. It simply depends on the decay constant of X. Decay constant is denoted by lambda. We will understand this later. And the second part of law of radioactivity states that the rate of disintegration of parent nuclei is directly proportional to the number of nuclei present at the moment. So rate of disintegration, rate, whenever it's associated, we will assume that time is into play. And rate of disintegration of parent nuclei here means the amount of parent nuclei that is going to disintegrate. So it's directly proportional to the number of parent nuclei present in the system at the moment. If we have larger number of parent nuclei, then we will get larger number of daughter nuclei. And if we have lower number of parent nuclei, then we will get lower number of daughter nuclei. It's that simple. Okay. So now we will be deriving the dating equation. Okay, so now we are going to derive the equation of radioactivity using the law of radioactivity. So basically what we came to know was minus rate of change of parent nuclei is directly proportional to the concentration of parent nuclei, isn't it? If I'm going to if I'm going to cook rice, so the amount of rice cooked will be dependent on the amount of rice I put into the cooker, isn't it? But don't use this analogy in radioactivity. So I'll start deriving. So we can first simplify this by sending the negative sign on the right and removing the proportionality constant, which will give the equation as dp by dt is equal to minus lambda of p. Okay, lambda is decay constant. So we can send p to the denominator and simply we can send this is dt. We can send dt to the numerator of RHS. So now the equation will look like this: dp by p is equal to minus lambda dt. So we will integrate both the sides, and for LHS we will integrate it from P to P naught, P naught to P, and RHS we will integrate it from 0 to T. Okay, so LHS will become ln of P, changing from P to P naught, and similarly the RHS will become uh, lambda T minus lambda T which is changing from 0 to T, isn't it? So on simplifying, the LHS will become ln of P P naught minus ln of P. I will draw a line to make it clear. Ln of P, which is equal to minus lambda of T. Okay, T equals to 0 is 0, and T, when we change it to T, will become T. So using the law of log, we can also write this as ln of P naught by divided by P. This is a whole single term. Then here we can we will write lambda minus lambda T. Now minus is very important. It will help in understanding the graph. Okay, so yeah, taking e both sides. Now we will take exponent both sides. So ln of e of ln is 1. Okay, e raised to the power ln is nothing but the same thing, 1. So we can write the LHS as p naught upon p, whereas the RHS will become e raised to the power minus lambda t. These are nothing but simple mathematical identities and operations. Okay, so for p naught we can write it as p raised to the power e minus lambda t. Okay, so this is our dating equation. Okay, so this will become this. No, oh, actually I did a mistake. Actually it should have been P naught and this should have been P. So please correct this. This is going to be P and this is going to be P naught. Okay, simply this is going to be P and this is going to be P naught. That's a very silly mistake which I did. This is going to be P, this is going to be P naught. Now the equation will change to P equals to P naught e raised to the power minus lambda, or I'll rewrite it as P equals to P naught e raised to the power minus lambda t. But this is actually not the dating equation that we use in field, because whenever we are in field, we can't obtain P naught. P naught is the initial concentration of the radionuclide parent. Okay, so we don't have that. After radioactive disintegration, it will become P. So we don't use this equation. So in the next class, we'll learn about what is actually the dating equation and what are its implications and how to read its graph. So first I'll summarize it up over here. That's all from my side. Thank you.